Hello everyone, I am Swarna Latha, working as assistant professor in the Department of Electronics and Communication Engineering. In today's lecture, we are going to discuss about the power density spectrum of the system response and the cross power spectral density of the system input and output. In the previous lecture, we have seen about the autocorrelation function of the system response, as well as we have seen the cross correlation between the input and output of the system. And moreover, we have discussed about the linear time invariant system. What is linear time invariant system? And we have seen the response of the LTI system. After that, we have calculated the autocorrelation function and cross correlation function of the system response and the input. In today's lecture, we are going to discuss about the power spectral density of the system response and the cross power spectral density of the system input and output. Now, if you know the autocorrelation function of the system input. So, what is the system? For example, this is an LTI system with the impulse response of h of t. Now, for this system, what I am applying here? I am applying a random process, a random signal x of t. Then, if I apply a random process to the LTI system, then it is producing a new random process output. It is producing a new random process output if apply a random process to the LTI system. And if the impulse response of this LTI system is h of t, then what is the response of the output of the system? That is nothing but y of t is equals to x of t convolution h of t, which have been discussed in the previous lecture. And we have, if you know the correlation function of the input signal, that is nothing but here what is the input here? X of t. Then what is correlation function? R xs of t comma t plus tau. So since we are taking the same input, then it is called as what? Autocorrelation. Now, if we know the autocorrelation function of the system input, then we can calculate the autocorrelation function of the system output, that is nothing but what? Ryy of tau. In case of it is a wide sense stationary random process, it will depend upon only the time difference. So, the autocorrelation function of the system response is nothing but what? Ryy of tau. So, this can be calculated by using the autocorrelation function of the system input. And similarly, we can calculate the cross correlation between the input and the output of the system. If you know the autocorrelation function of the system input, and similarly you can calculate the cross correlation between the output and input, that is nothing but Ryx of tau. So, these relations already we have discussed in the previous lecture. So, Ryy of tau in terms of Rx of tau, and similarly Rxy of tau and Ryx of tau in terms of the autocorrelation function of the input. So this is we have discussed in the time domain. And the similar manner, if you want to know the spectral characteristics of the system response, then you have to apply the Fourier transform. So, spectrum is nothing but frequency only. So, spectrum is nothing but frequency. So, how do you convert a signal from time domain to frequency domain? By applying Fourier transform. So, in the previous lecture, we have seen the characteristics of the system in time domain. What are the characteristics we have seen? We have seen the statistical characteristics, like we have seen the mean square of the system response, and have seen the autocorrelation function of the system response, and then you have seen the cross correlation between the input and output, and similarly the cross correlation between the output and input. So these all we have discussed in the time domain. In today's lecture, we are going to discuss these properties in frequency domain by applying Fourier transform to these functions. So, and how we have calculated the cross correlation of the output and the cross correlation of the output and input, and cross correlation of the output. If we know the autocorrelation function of the input. In the similar manner, if you know the power spectral density of the input, so what is the power spectral density of the input? Sx of omega. Then you can calculate the power spectral density of the output. What is the output here? Y of t is your output or response. So what is the power spectral density of the output or system response? That is nothing but what? Syy of omega. So this is called as what? The power spectral density of the system response. And similarly, Sxy of omega, that is nothing but what? Xy. If you take two different, then you have to call it as what? Cross. So cross power spectral density of the system input and system output. And here Syx of omega, nothing but the cross. Since you are having two different signals, nothing but cross. The cross power spectral density of the output and input. So these three can be calculated by using the power spectral density of the input. So like that, if you know the characteristics of the input in the time domain and the frequency domain, then you can calculate the spectral characteristics as well as the statistical characteristics of the system response in terms of the input. And if they have given the transfer function of the system. What is the transfer function? H of omega is called as the transfer function. That is nothing but what? Y of omega by x of omega. Or H of s is equals to Y of s by x of s in terms of S domain. This is in terms of what? Frequency domain by applying the Fourier transform. And already in the previous lecture, we have seen the relation between the power spectral density and autocorrelation function. What is the relation? That relation is called as what? Wernier-Kinchen relation. The relation between the power spectral density of the system as well as the autocorrelation function, then it is called as what? Wernier-Kinchen relation. Now, what is this Wernier-Kinchen relation states that? The Wernier-Kinchen relation states that the Fourier transform of the autocorrelation function for a wide-sense stationary random process is nothing but the power spectral density of the function. So, what is the relation states that? The Fourier transform of the autocorrelation function. So, Fourier transform is nothing but what? Ft. Fourier transform of what? Autocorrelation function of a wide-sense stationary random process. For example, if I consider x of t is a wide-sense stationary random process. Already we have seen what is wide-sense stationary random process. A random process is said to be wide-sense stationary if it satisfies two conditions. The first condition is nothing but the mean of the random process should be constant. Nothing but expectation or E of x of t is equals to constant for all the values of t. And the second condition for a wide-sense stationary random process is the autocorrelation function will depend upon only the time difference only. These are the two conditions to be satisfied for a wide-sense stationary random process. So consider x of t is a wide-sense stationary random process. Then what is the Wernier-Kinchen relation states that? The Fourier transform of autocorrelation. Whenever I say correlation, you have to write down R. Correlation nothing but relation R. Then auto means you have to take the same signal only. So same process only I am taking here. Here I am considering the random process x of t. Therefore here Rx. Next, since I am considering that it is a wide-sense stationary random process, it should be a function of only the time difference, not dependent upon t. Depends upon only the time difference only. Therefore, the Fourier transform of the autocorrelation of the random process x of t, which is a wide-sense stationary, is equal to what? The power spectral density or the power density spectrum. So, what is the power density spectrum of the random process x of t? So, whenever I say spectral density, you have to represent by S, and power spectral density function nothing but, since it is the same signal, you have to take what? Xx. If it is cross means you have to take two different signals. If it is power spectral density, auto power spectral density, simply called as what? Power spectral density. Then you have to consider the same random process only. So yes, x of omega. Here what is omega represents? Omega represents the angular frequency. That is nothing but what? 2 pi f. So this is a Wiener-Kincher relation which is very important. So it says that the Fourier transform of the autocorrelation function is equal to the power spectral density. Now what is the Fourier transform formula? So we know that the Fourier transform of a function f of x, let us say. Then what is formula? Integration minus infinity f of x into e power minus j omega x dx. So this is a Fourier transform formula. Now what I want here, I want the Fourier transform of Rx of tau. In place of f of x, now I have Rx of tau. Then what is Fourier transform formula? Integration minus infinity. So in place of f of x, what I have here? Rx of tau. So Rx of tau into e power minus j omega tau d tau. So in place of x variable, I have the variable tau. So replace x by tau. So therefore, what is the power spectral density as x of omega is equals to integration minus infinity Rx of tau into e power minus j omega tau d tau. So if x of t is a wide sense change random process and it is applied to the system, LTA system. Now, in the similar manner, I can write down the power spectral density of the system response y of t. So, what is the power spectral density of the system response y of t? So, if it is input x of t, then it is nothing but sx of omega. If I want to calculate the power spectral density of the system response or the output of the system y of t, then it can be represented by s y of omega is equals to what? Integration minus infinity. So since of the output and what is the autocorrelation function of the system response? There is nothing but Ryy of tau. So Ryy of tau into e power minus j omega tau d tau. And what type of input I am giving here? I am giving a random process x of t which is wide sense stationary, and this I am applying to the system. If I apply a random process which is wide sense stationary to LDA system, then its response is also a wide sense stationary random process. That's why its autocorrelation function is the function of only the time difference. So this is a Wiener-Kincher relation states that. Now, in the previous lecture we have seen the autocorrelation function of the system response. How did we get this one? This expression. So what is y of t is equals to x of t convolution h of t, because this I am applying to a LTA system, and for this LTA system the input is x of t and its response is y of t, and its impulse response is h of t. Then what is y of t is equals to, you can write down the expression as x of t convolution h of t, or else you can write down this as h of t convolution x of t. But what I want here, I want the autocorrelation function. So what is autocorrelation function? Ryy of tau. So Ryy of tau, nothing but what? T comma t plus tau. If it is wide sense stationary, then in place of t comma t plus tau, we'll get only the time difference. So t plus tau minus nothing but what? Tau is equals to what? Expectation of y of t into y of t plus tau. So what is the autocorrelation function formula? Is nothing but expectation of the product of two functions. One is the given function y of t and its delayed function y of t plus tau. Now replace this y of t by what? X of t convolution h of t, or else you can replace it by h of t convolution x of t. And then if you simplify, you'll get the expression like this. This is already we have derived in the previous lecture. Now what is the expression we got? We got the expression as what? Ryy of tau is equals to integration minus infinity and integration minus infinity Rxs of tau plus lambda 1 minus lambda 2 into h of lambda 1, h of lambda 2, d lambda 1, d lambda 2. Here Rx of tau plus lambda 1 minus lambda 2 represents the autocorrelation function of the input x of t at the time difference and the time instant tau plus lambda 1 minus lambda 2. And this h of lambda 1, h of lambda 2 represents the impulse response of the system. Now, so from the previous expression, if I know the autocorrelation function of the output, then how can I calculate the power spectral density of the output? By using this linear interrelation. So what is this? This is nothing but what? The Fourier transform of the autocorrelation function. Now replace this Ry of tau by this expression in this equation. So what is Ry of tau? That is nothing but integration minus infinity, integration minus infinity, Rx of tau plus lambda 1 minus lambda 2 into h of lambda 1, h of lambda 2, d lambda 1, d lambda 2. So this is nothing but what? Y of tau. So, and this Fourier transform nothing but what? Integration minus infinity e power minus j omega tau d tau, which gives you power spectral density of the output. Now in this you consider this function tau plus lambda 1 minus lambda 2 equals to lambda. Now, so from this tau plus lambda 1 minus lambda 2, tau plus lambda 1 minus lambda 2 equals to lambda. So from this what is tau is equals to lambda minus lambda 1 plus lambda 2. So replace this tau in this expression, tau plus lambda 1 minus lambda 2 by lambda. Then what do you get here? Rxs of lambda into here in place of tau. What do you get here? Lambda minus lambda 1 plus lambda 2. So lambda minus lambda 1 plus lambda 2. Then d tau is equals to what? D lambda. Because these two are constants, that's why d tau is equals to d lambda. Then we can get the expression as integration minus infinity, integration minus infinity, Rxs of lambda into h of lambda 1, h of lambda 2. Next you are having d lambda 1, d lambda 2. You can write down this expression as what? E power minus j omega lambda into e power minus j omega into minus lambda 1 into e power minus j omega lambda 2 d lambda. Now rewrite down this equation as integration minus infinity to infinity, Rxs of lambda into e power minus j omega lambda into what? D lambda. So again integration minus infinity. Next h of lambda 1 into here what is lambda 1 expression here? This one. So e power minus j omega into minus lambda 1 d lambda 1. Next remaining expression integration minus infinity h of lambda 2 e power minus j omega lambda 2 d lambda. So d lambda 2. So h of lambda 2 into e power minus j omega 2 lambda 2. So there is nothing but what? Fourier transform formula. What is the Fourier transform formula? Previously we have seen Fourier transform of f of x is equals to what? Integration minus infinity f of x e power minus j omega x dx. And nothing but what? F of omega is equals to what? Integration minus infinity f of x into e power minus j omega x dx. Now we will see in place of f of x what do you have now. Now in place of f of x now I have Rx of lambda. That is nothing but what? Fourier transform of Rxs of lambda into next what is this? So this is nothing but what? Fourier transform of h of lambda 1. But in place of plus you have here minus lambda. What is the Fourier transform of h of lambda is h of omega. But in place of plus you are having minus. Therefore what do you get here? H of minus omega. So here, so this is nothing but what? H of minus omega into here integration minus infinity h of lambda 2 into e power minus a omega lambda 2 d lambda 2. So what is this? Nothing but what? H of omega. So you can rewrite down this as what? E power minus j minus omega into lambda 1. So in place of plus omega, you are having minus omega. Therefore in place of plus omega, you are going to get minus omega. So what is the expression you got here? Fourier transform of Rx of lambda into h of h of minus omega into h of omega. So that equals to, what is the Fourier transform of Rx of lambda? So from the Fourier-Kinshasa relation, what does it say, sir? The Fourier transform of the autocorrelation function gives the power spectral density. Therefore, what is the Fourier transform of the autocorrelation function of the input? It is given the power spectral density of the input Sx of omega. Now you just replace this equation, then it is nothing but what? Sx of omega. Now what is h of minus omega? Is nothing but what? From complex conjugate property of the Fourier transform. Then what is h of minus omega? Is nothing but what? H star of omega only. So that equals to Sx of omega. So now what is a star into a? Nothing but what? Mod of a square. For example, a equals to some x plus iy. And what is a star equals to? Complex conjugate. Nothing but x minus iy. Then what is a star into a? That's nothing but x minus iy into x plus iy. That is nothing but what? Square root of x square plus y square. So x minus iy and x plus iy. So what you are going to obtain here? You are going to obtain here x square plus y square. That is nothing but what? Mod of h of omega square only. Here that is nothing but what? Mod of a square. What is mod of a? Mod of x plus I whole square. Then nothing but x square plus y square. Therefore, what is h star of omega and h of omega? Then nothing but mod of h of omega square. Therefore, the power spectral density of the system response Syy of omega is equals to Sxs of omega into mod of h of omega square. So this is the expression we got. So if you know the power density spectrum of the input and what is mod of h of omega square, nothing but what? The power of the transfer function. Nothing but what? The power of the transfer function, because h of omega is called as what? Transfer function, the square of the transfer function. So if you know the power density spectrum of the input and the transfer function has been given, then you can calculate the power spectral density by using this relation. What is the relation? Syy of omega equals to Sx of omega into mod of h of omega square. So where Sx of omega gives what? The power spectral density of the input, and h of omega is a transfer function of the system. So like that you can calculate the power spectral density of the system response. What is the power spectral density? Nothing but it gives how the power has been distributed with respect to the frequency. Now, after that we are going for cross power spectral density of the input and output. So this is the system, LTI system, and for this LTI system we are applying the input random process x of t, and the impulse response of this LTI system is h of t. Then its corresponding output is y of t. Again it is also a new random process only. Then if you want to calculate the power spectral density, so spectral density nothing but what? S. The power spectral density represented by S. And what I want here? Cross. Cross is nothing but cross between two signals. The two signals have to take input and output. Here what is input? X. And what is output here? Y of t. So it has been represented by what? Sxy of omega. This I have to calculate now. Now, how do you calculate the power spectral density of the cross power spectral density of the input and output? And similarly, you can calculate the cross power spectral density between the output and input also. So this can be calculated by knowing the cross correlation between the input and output, and the cross correlation between output and input. By taking a Fourier transform of this, we are going to get the cross power spectral density, because the relation between correlation and power spectral density both form a Fourier transform pair. Therefore, if you know the cross correlation functions, then you can calculate the cross power spectral density. Now, what is Rxy of tau represents? It represents a cross correlation between input and output. What is correlation? That is nothing but measuring the similarity. And what is ROX of tau? Represents a cross correlation between output and input. So this expression already we have derived in the previous lecture. What is expressions we got? Rxy of tau is equals to Rx of tau convolution H of tau. And similarly, what is ROX of tau is equals to Rx of tau convolution H of minus tau. What is convolution formula? Integration minus infinity Rx of lambda into H of t minus lambda minus tau d lambda. So this is a convolution formula. Now here in place of plus tau, what do you have here? Minus tau. Only that's the difference. So this expressions already have derived in the previous lecture. So and how do you get the power spectral density? By taking the Fourier transform of cross correlation function of the input and output, and similarly cross correlation function of the output and input. You are going to get the cross power spectral density of the input and output as well as the output and input. Now the Fourier transform of the cross correlation function of the input and the output. The system response is equals to what? Fourier transform of, previously what is the expression we got? Rx of tau convolution H of tau. So Rx of tau convolution H of tau. Now we know the property of Fourier transform. What is the property here? You have to recollect convolution property. What is the convolution property? States that if you have two signals x of t and h of t, so and the convolution of those two signals in the time domain gives multiplication in the frequency domain. So in the frequency domain, what is x of t? X of omega. In the frequency domain, what is h of t? H of omega. So convolution is giving in the time domain, gives in the multiplication in the frequency domain. So you can substitute the property here. Therefore, the Fourier transform of convolution of the autocorrelation function Rx of tau into and with respect to the h of tau. There is nothing but what? Fourier transform of, there is nothing but here Fourier transform of Rx of tau into Fourier transform of h of tau. Now what is the Fourier transform of the autocorrelation function of the input, which gives a Wiener-Kincher relation? What is that? States that the Fourier transform of the autocorrelation function gives a power spectral density. Therefore, the Fourier transform of Rx of tau is equals to what? Sx of omega into what is the Fourier transform of the impulse response h of tau? Then nothing but the transfer function h of omega. Fourier transform of h of tau is equals to h of omega. So like that you can calculate the power spectral density of the input and output. It means if you know the power spectral density of the input and if you know the transfer function, then you can calculate the power spectral density between the input and output of the system. And similar manner, if you want to calculate the power spectral density between the output and input, then how do you calculate this? By using the cross correlation between the output and input. Now already we have seen the expression for cross correlation between the output and input, that is nothing but Rx of tau is equals to what? Rx of tau convolution h of minus tau. Now just by applying Fourier transform for this equation, we are going to obtain the required expression. Then the Fourier transform of Rx of tau is equals to Fourier transform of Rx of tau convolution h of minus tau. Again the same property, by using the convolution property of the Fourier transform, you can write down here the Fourier transform convolution in the time domain is giving multiplication in the frequency domain. And there is nothing but what is the frequency domain of Fourier Rx of tau? Nothing but Fourier transform of Rx of tau. And the frequency domain is given the multiplication. So into Fourier transform of h of minus tau. Now what is the Fourier transform of h of minus tau? This you have to recollect the property from Fourier transform. That property name is time reversal property. What is the property? Says that the Fourier transform of the reversal of the signal gives the reversal in the time domain, frequency domain also. There is nothing but what? X star of omega. And similarly, what is the Fourier transform of h of minus tau? Then nothing but h of minus omega. Therefore, this is the expression for finding the cross power spectral density between the output and the input of the system. Now, if you know the power spectral density of the output, then how do you calculate the average power? What is the expression? This expression already have derived. We have seen in the previous lecture. What is the expression you got? Pyy is equals to nothing but the average power. So the average power of what? The response of the system y of t. Pyy is equals to what? 1 by 2 pi integration minus infinity syy of omega d omega. Here what is syy of omega? It represents what? The power spectral density of the output y of t. So how, if you know the power spectral density of the output, then how do you calculate the average power contained in the output random process y of t? For that, what you have to do? There is nothing but what? 1 by 2 pi times. So this represents the area. So 1 by 2 pi times the area under the power spectral density of the output y of t. So this is the relation between the power spectral density and the average power. Now by using these relations, we'll see one example. So calculate the power density spectrum and the average response of the network system as shown in figure if the input to the system applied is white noise, whose power spectral density is given by Sx of omega is equals to n naught by 2. So since it is white noise, the power spectral density is constant, which is Sx of omega equals to n naught by 2. So what they have given that? They have given the power spectral density of the input they have given, and they have given the network. So for this network, and what you have to calculate? You have to calculate the power density spectrum of the output. Response is nothing but what? The output. Here, what is output here? Y of t is your output. You have to calculate what? You have to calculate syy of omega equals to what? How do you calculate? How do we have seen the expressions here? The power spectral density of the output syy of omega is equals to what? Sx of omega into mod of h of omega whole square. Now write down the formula here. What is the formula here? Syy of omega is equals to Sx of omega into mod of h of omega square. So here they have given the power spectral density of the input. Now instead of giving the transfer function directly, they have given the network system. Now for this system, you have to calculate the transfer function. How do you calculate the transfer function for the system? Since it is an electric circuit, and let us consider the current flowing through this circuit is I of t. Then you apply this KVL. Then what is the expression going to get? X of t is equals to what? X of t is equals to what is the voltage across the inductor? Nothing but what? L into di of t by dt plus what is the voltage across this resistor? Since the current is I of t, then what do you get here? R into I of t. Now what is this R into I of t? That is nothing but here y of t. That is nothing but what? Y of t. So what is y of t equals to? The output voltage. That is nothing but the voltage across the resistance R. So how do you calculate the voltage across this resistance R? The current is I of t. So R into I of t. So R into I of t. Now what is I of t from this? Y of t by R. Y of t by R. Now you substitute here, then what can you obtain here? X of t is equals to L into d y of t by dt. So since R is constant, rider has 1 by R into y of t. So here 1 by R, nothing but L by R. Plus here R into I of t, nothing but what? The voltage across the resistance. Nothing but here y of t. Now if I want to calculate the transfer function, then what I have to do? I have to apply the Fourier transform on both sides. Then what is the Fourier transform of x of t? Then nothing but what? X of omega is equals to L by R into what is the Fourier transform of dy of t by dt? For this, what you have to do? You have to recollect the differentiation property of Fourier transform. What is the differentiation property? States that if the Fourier transform of x of t is x of omega, then the Fourier transform of dx of t by dt equals to j omega into x of omega. It means, what is the property says that differentiation in the time domain gives multiplication in the frequency domain. Therefore, here also you get j omega into the Fourier transform of y of t is what? Y of omega plus, what is the Fourier transform of y of t? Y of omega. Now from this, you just take common y of omega, then you are going to obtain L by R plus 1. That equals to, you take the LCM, then you will get L plus R by R. That is nothing but what? X of omega. So from this, y of omega by x of omega. Right? And because it gives a transfer function. So y of omega by x of omega. What do you get here? So bring this x of omega here and this to the LHS side. Then you are going to get R by here j omega L. Sorry. Here this is j omega L. So R by R plus j omega into L. So that equals to, if you take R common, then what can you obtain here? 1 plus j omega L by R. Therefore, this is a transfer function of the given network. Now, if you know the power spectral density and if you know the transfer function of the given system, then the power spectral density of the output, the response of the system is nothing but Sx of omega into mod of h of omega square. What is Sx of omega they are given? It is a white noise whose LPS is n0 by 2. So, n0 by 2 into mod of, what is the transfer function of the system? 1 by 1 plus j omega L by R. Now, you substitute here Sx of omega into mod of h of omega square. Then, what is here? Sx of omega nothing but n0 by 2 into, what is the transfer function we got here? 1 by 1 plus j omega L by R. So, 1 by 1 plus j omega L by R whole square. That equals to n0 by 2 by, and what is mod of 1 plus j omega L by R? Nothing but, if you simplify this, then what are you going to obtain here? So, nothing but what? You can have to rationalize this one. So, if you rationalize, then what you are getting here? Multiply with 1 minus j omega L by R, and here also 1 plus j omega L by R into 1 minus j omega L by R here. And then you have to take what? Modulus. That equals to what? And n0 by 2 is constant. You can write down here. So, mod of 1 minus j omega L by R by, so a plus ib into a minus ib. What are you going to get here? A square plus b square. So, 1 plus omega square L square by R square. So, that equals to, then what is mod of 1 minus j omega L by R? That is nothing but what here? So, and then you have to take the square. So, after that you have to take the square of the total thing. Then you are going to get here square. You have to make the square. Then mod is what? Mod of 1 minus j omega L by R, that is nothing but 1 plus omega square L square by R square by 1 plus omega square L square by R square whole square. Then we are going to get here into n0 by 2. So, you are going to get what? n0 by 2, and here this will be cancelled, and 1 plus omega square L square by R, that is nothing but omega L by R whole square. Therefore, this is the power spectral density of the response of the given network system. And moreover, what you have to calculate? You have to calculate what? The average response of the network. So, nothing but the average power of the response of the network. So, what is the average power formula? Pyy is equals to what? 1 by 2 pi integration minus infinity syy of omega into d omega. So, what is syy of omega? Already we have calculated here. n0 by 2. So, what do you get here? Syy of omega equals to 1 by 2 pi integration minus infinity. Then syy of omega. What is that? n0 by 2 by 1 plus omega L by R square into d omega. So, since n0 by 2 is constant, you can bring it outside. Then you can rewrite the expression as n naught by 4 pi integration minus infinity 1 by 1 plus omega L by R square d omega. Now we know that. So next what you have to do? You have to assume that omega L by R equals to tan theta. From this, what is omega equals to? R by L into tan theta. Then what is d omega equals to? R by L is constant and differentiation of tan theta is what? Secant square theta. And here what do you get here? So 1 by 1 plus, what is omega L by R here? Tan theta. So 1 by 1 plus tan square theta. And what is d omega is equals to R by L into secant square theta. So R by L into secant square theta. Then what is into what? D theta. So R by L secant square theta into d theta. And what about the limits here? Here omega limits are minus infinity and plus infinity. Then what about the theta limits? If omega equals minus infinity, then what is theta equals to? Minus pi by 2. So when omega equals minus infinity, theta limit is minus pi by 2 because tan pi by 2 is infinity, tan minus pi by 2 is minus infinity. And similarly, what about when omega equals infinity, then if omega is infinity, then what about that theta limits? Plus pi by 2. So plus pi by 2. And if you substitute here, then you are going to obtain n naught into r by 4l. N naught by r into 4l because 1 by 1 plus tan square theta and 1 secant square 1 by secant square theta. So secant square theta will get cancelled. Then you are going to get here 1 and bring this r by l to the outside. And integration of 1 plus for theta or the limits minus pi by 2 gives what? Pi. So then pi will be get cancelled. Then you are going to get what? N naught into r by 4l. So like that you can calculate the power spectral density of the system response if they have given the power spectral density of the input and the transfer function. And similarly, you can calculate the cross power spectral density of the system input and output if you know the power spectral density of the input and the transfer function. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.